Hi everyone, welcome to our video recording for section 8.2, dealing with integration by parts. Now in this video, we're going to be using integration by parts when appropriate to evaluate certain integrals. In addition to this, we're also going to be taking a look at integrals that require us to use repeated integration by parts, and I'll show you guys a shortcut for those. And lastly, we're going to be solving application problems where we need to use integration by parts. Alright, so what is integration by parts? Well, integration by parts is a technique that allows us to deal with integrals involving products. So in a sense, you can think of the integration by parts technique as being analogous to the product rule for derivatives. Now with this idea in mind, let's go back and recall the product rule. So let's say that I had two functions here, u times v, and I want to figure out what was the derivative of u times v. Well, according to the product rule, the derivative here is going to be the derivative of the first function times the second plus the first function times the derivative of the second. So there we go. This is the product rule. Now you might remember saying the product rule in terms of f times g's, but this is the same idea here, just switching the variables a little bit. Alrighty, so here's the product rule. Now let's say that we want to integrate the product rule so we can go back to the original function. Alright, so if I'm integrating the derivative, remember that we essentially go back to the original function. So we're going to have here a u times v. There we go. We went back to the original function. But what about the right-hand side though? Well, integrating the right-hand side, we're going to obtain the integral of u prime times v dx plus the integral of u times v prime dx. Now at this point, I want you to recall a little bit about our knowledge for differentials. If I see here a u prime dx, well, recall that that is our definition for du. Du is the same thing as u prime dx, and on the other integral, we have a v prime dx. Well, v prime dx is the same thing as the differential dv. Okay, so rewriting our integrals here in terms of du and dv, we're going to obtain the following. The integral of v du plus the integral of u dv. Now with this equation ready, I'm going to go ahead and solve for the integral of u dv, which is going to give us the integral of u dv is equals to u times v minus the integral of v du. And there we go. This is going to be the formula that we're going to be using for integration by parts. Alright, now I want you guys to note here that whenever we're dealing with an integral of the form u dv, we're still going to need to evaluate an integral of the form v du. Alright, now with that said here, let's take a look here at a couple of pointers and some suggestions that I'll give you. Alright, so as we discussed above, the integral of u dv is the same thing as uv minus the integral of v du. Now, I want you guys to note here that integration by parts, although it is very useful, it should only be considered after first considering a straight u substitution. So if you try a u substitution and it doesn't quite work, alright, then let's go ahead and see if maybe integration by parts will work. Alright, so if we're going to be using integration by parts, how do we know how to define the dv and how to define the u? Well, typically a good starting point is to let dv be the most complicated portion of the integrand that fits, and this is very important, a basic integration rule. Since you're going to be obtaining a v from the integral of dv, you want to make sure that you're able to integrate the dv. Now, once you define the dv, then u will be the remaining factors for the integrand. Now, another alternative, and this is typically the one that I use, I begin by defining the u to be a portion of the integrand whose derivative is a function simpler than the u. Now, what I mean by this here is, let's say that we had a polynomial, I don't know, x cubed. Well, the derivative of x cubed is 3x squared, which is something simpler than the cubic. Now, if that's the case, then dv will be the remaining factors of the integrand. Now, this is typically how I define the u and the dv, but I know that some people like to use the following acronym to define their u's. The acronym is LIATE, which stands for logarithmic functions, inverse trigonometric functions, algebraic functions, trigonometric functions, and lastly, exponential functions. Now, typically you want to use, or whichever function comes first, you want to define that as your u. However, I would mention that this is not a hard and fast rule. Sometimes it works. I mean, a lot of times it works, but not always. Alright, so with that in mind, guys, now that we've seen the formula, we've seen some hints as to how we can go ahead and define our u and dv, let's go ahead and take a look at some examples here because nothing really beats practice. All right, so let's say that we're trying to figure out the integral of x times e to the 3x. Now this one here doesn't seem particularly complicated, so our first guess might be to go ahead and use a u substitution. I mean, that's worked most of the time here. So I'm going to go ahead and define the u as 3x, so we get our du equals to 3 dx. Uh-oh, well, our du only has a 3, but the integral itself here has an x. We can't get an x anywhere, so a simple u substitution doesn't quite work. So let's go ahead and use integration by parts. Now, since we've seen a formula for the first time, I'm going to go ahead and rewrite the formula for the integration by parts again. So with the integration by parts, it says that the integral of u dv is equals to u times v minus the integral of v du. Alrighty, so now this is the first example for us to define the u. Alright, now a distinction here between the u's that we're going to be selecting now and the u's that we selected in the past is that the u's that we selected in the past for a u substitution was typically a u that was involved in a function composition. But right now, the u's are going to be functions that are making up a product inside the integrand. So our choices for u right now are going to be the x or the e to the 3x. Now, which one seems that it's probably going to be simpler? Well, I'm thinking that the u that's going to be simpler is the x because the du is simply going to be a 1 dx. Alright, so if that's our u, then the other factor here, or the other part of the product inside the integrand, is dv equals to e to the 3x dx. Now notice here that I'm including the dx here because we're talking about a dv here. Alrighty, now this is where we're going to be integrating the dv to figure out what's the v here. Alright, so we're dealing here with the integral of e to the 3x dx. This is the importance of the dx above. Now, at this point, I trust that you guys feel more comfortable figuring out what is the integral of e to the 3x. Now this one here is going to be a 1/3 e to the 3x. Now if there's any question about how we're getting or how I'm getting this 1/3 e to the 3x, feel free to ask me, send me a message, or you can always go ahead and visit the tutoring centers. Alrighty, so we get our u, we get our dv, so I'm just going to go ahead and label them here. If we have the integral of u, I'll put here, there we go, the integral of u dv, well, we know that this is going to give us u times v minus the integral of v du. Alrighty, now this is where we're going to be putting everything together here. So we're going to have the integral of x times e to the 3x dx is going to be equals to our u times our v minus the integral of v du. Alrighty, now at this point here, now notice that again, whenever we're using integration by parts, we're going to have another integral to solve. But this time around though, the integral that we're solving, the v du, is a much simpler integral. Now for this one here, I'm going to go ahead and rewrite it a little bit. So I'm going to go ahead and take the 1/3 outside. So really we're just dealing with the integral of e to the 3x, which is, lo and behold, the same integral that we just did. So we're going to get here a u times v, which was the x times 1/3 times e to the 3x. So we're going to have a 1/3 x e to the 3x minus a 1/3 times the integral of e to the x dx, which I'll put here in plum, which is going to be another 1/3 e to the 3x. And now we add the plus c. Now notice here that when I performed the integral of dv, we didn't really add a plus c because, well, since we're going to be dealing with another integral here, at the end, we're going to add a constant regardless. So there's no need to include the integral, there's no need to include the c whenever you're evaluating the integral of dv. Alright, now to simplify things and get our final answer, we're going to get the integral of x times e to the 3x dx is going to be equals to 1/3 x times e to the 3x minus, now we're going to have here a 1/3 times 1/3, so it's going to give us here a 1/9 e to the 3x plus c. Now, since we're using integration by parts for the first time, well, we gotta make sure that it works. So let's go ahead and check. If we were to take the derivative of our answer, well, we should be getting back the integrand. So let's see. All right, so if we take the derivative of 1/3 x times e to the 3x, notice that we're going to be using the product rule here. Well, that's going to give us here a 1/3 times the derivative of x, which is 1 times e to the 3x, plus x times the derivative of e to the 3x, minus 1/9 times the derivative of e to the 3x, plus the derivative of c, which is 0. Whoops, missed the parentheses here. There we go. Now, simplifying the derivative, we're going to get 1/3 e to the 3x plus x times e to the 3x minus 1/3 e to the 3x, which allows us to cancel the positive 1/3 e to the 3x. And there we go. What are we left with? Well, we're left with x times e to the 3x, which, there we go, is our integrand. So there we go. Alrighty, so this was one example here of integration by parts. Let's go ahead and take a look at another one here. Alright, so for this next example, we're being asked to find the integral of the ln of x over x squared with respect to x. Alright, so taking a look at this problem here, but do we need integration by parts? I mean, I don't know, maybe. We should always see if we can maybe just use a straight u substitution to see if that gets the jobs done. So if I take a look at this one here, I'm thinking that, okay, a possible choice of u would be the ln of x. So now our du would be a 1 over x dx. And oh no, it seems like a normal u substitution is not going to work. So maybe we can try integration by parts. If we try integration by parts, which one should be our u, which one should be our dv? Well, if we take a look at some of the hints here, with the acronym of LIATE, we can think that, okay, well, maybe we can let the logarithmic functions represent our u. Alright, so that's what I'm going to do here. I'm going to keep the same u, but this time around, though, we're using integration by parts. Okay, so that means that now we have to figure out what is our dv. Now we got to be careful here, because we're thinking of the dv here as the other part of the product, not any sort of function composition. So for this one here, if our u was the ln of x, then our dv has to be the 1 over x squared dx. Okay, so now we need to figure out what would be our v. So our v is going to be equals to the integral of 1 over x squared dx, which is equals to negative 1 over x. Alright, so now that we defined the u and the dv as well as the v and the du, let's go ahead and use integration by parts to figure out this integral. So we're going to have then the integral, well, since it's the same line, I'll keep it here. So the integral of the ln of x all over x squared with respect to x is equals to our u times our v. So we're going to get a negative ln of x over x minus the integral of our v du. Alright, so we're going to now get, let's see, it's going to be a negative ln of x over x plus the integral of 1 over x squared, but lo and behold, what we just did, the integral of 1 over x squared. So then our final answer here, putting everything together, is going to be a negative ln of x over x minus 1 over x plus c. And there we go. Alright, so now let's take a look at this next example, where we're being asked to find the integral of the arcsine of x. Now, we already dealt with the inverse trigonometric functions before, but we never really discussed their integrals. In part of the reason was because, well, we were not ready how to actually find them. But now, with the integration by parts technique, we're able to find this integral. So let's take a look. Now, this one here might look a little bit weird because it doesn't quite seem like we have a product of two functions. However, whenever something like that happens, the easiest thing to do here is simply define the u as, well, your main function here, the arcsine of x, and the dv will simply be dx. And there we go. We have here our product, the arcsine of x times, quote unquote, times dx. Alright, so now let's go ahead and use integration by parts. So let's see, figuring out our du, we're going to get that the du here is the derivative of the arcsine, which is 1 over the square root of 1 minus x squared dx. And figuring out our v here, well, that's pretty straightforward. The integral of 1 dx here is just x. Alright, now putting everything together here then, the integral of the arcsine of x is going to be equals to our u times our v So it's going to be an x times the arcsine minus the integral of our v du. Okay, so now we're left with one more integral. So what is the integral of x over the square root of 1 minus x squared? Now, I don't think we need integration by parts for this one. For this one here, we can go ahead and use a simple u substitution. So this u here that I'm going to be defining is the u in the composition, which I'm going to let it be 1 minus x squared, and get to see here that our du is a negative 2x dx. Alright, so I'm going to go ahead and do this integral on the side here. So the integral of x over the square root of 1 minus x squared is going to be equals to the integral of, now substituting in our u's, we're going to have a u to the 1/2 power on the top, sorry, on the bottom. Now what about the top though? Well, you see here that on the top we almost have our du. Our du is negative 2x dx, but on the top we just have an x dx. We can go ahead and remedy that by multiplying by a negative 1/2 on the outside. So now we have a negative 1/2 times the integral of 1 over u to the 1/2 du. So this one here is going to give us a nice result here. We're going to get a negative 1/2 times a 2u to the 1/2 power. Alright, so canceling the 2's here. And substituting in our u's, we're going to get a negative square root of 1 minus x squared. Alright, now putting everything together, we're going to have here the integral of the arcsine of x is going to be equals to x times the arcsine minus, I'll put that minus here in red, minus, now the result from our integral was itself another minus, square root of 1 minus x squared. Alright, now the minus and a minus, I'll just turn it here into a positive. And lastly, a plus c. And there we go. Now we know what the integral of the arcsine is. Alrighty, now to finish this part of the video, I want you guys to take a look here at two integrals and compare them. Alrighty, so for the first integral, we have x times the sine of x dx, and the other integral here is the integral of x times the sine of x squared. Now taking a look at these two integrals, which one seems easiest? Now if you work with many u substitution problems, you might be inclined to think that maybe the second integral seems a little bit easiest, because considering the second integral, we can go ahead and define the u as the argument for the sine function. So if we define our u here as x squared, then our du is 2x dx. So you would see that we could rewrite our original integral in terms of u as 1/2 times the integral of the sine of u du. Now this integral here is going to give us a 1/2 times the integral of sine, which is going to be a negative cosine of u plus c. Now going back to our original variable, we're going to have then a negative 1/2 times the cosine of 2x plus c. Not too bad here. But what about the first integral where we had x times the sine of x? Could a u substitution work? Well, if we went ahead and defined the u as the argument of the sine again, if u is equals to x, well then you would see here that the u would simply be 1 dx, but we still have an x in front of the sine, so it doesn't quite work. Okay, well that's not a problem because, well, we do have a sine times an x. So it means that, okay, well there's a product, so maybe integration by parts would work. So let's see, let's go ahead and try integration by parts. Alright, so for this one here, which one is a better choice of u? The x or the sine of x? Now we can go ahead and maybe use the acronym Lyautey to figure out which one would be a better choice of u or dv, but again, I want to emphasize here that we don't need that acronym. We can also just think about, okay, well, if we define the u as the sine of x, our du would be a cosine of x, which itself is not a problem, but I mean, I would say it's not necessarily the sine and the cosine, yeah, they're pretty much the same thing. One of them is not necessarily simpler than the other. However, if we instead choose an x as the u, well then the du is 1 dx, much simpler. So I'm going to go ahead and define the u as x, then the dv is going to be equals to the sine of x. Alright, so if the dv is the sine of x, then the v is going to be equals to the integral of the sine, which is a negative cosine of x. Oops, I missed the dx here on the dv. Alright, so now that we define our u and the v, let's see then, the integral of the x times the sine of x is going to be equals to a negative x times the cosine of x minus the integral of a negative cosine of x dx. Now at this point here, we have a negative and a negative, so I'm just going to go ahead and get a positive here. Alright, so now the integral of cosine, we know that's a sine, so our final answer is going to be a negative x cosine of x plus the sine of x plus c. And there we go. So as you can see here, now before we really couldn't handle integrals like this, but now with integration by parts, we're ready to take them on. Alrighty guys, so this is it for this first part of the video. In the next video, we're going to be going over problems that involve repeated integration by parts. See you there.